Hello, and welcome to Weapons of Math Instruction. This is the 6th in our series of 7 videos celebrating Pi Day. If you missed the first 5, you can find them on my YouTube channel or my Facebook page. In this video, we'll be looking at the Wallis formula for pi. In the first segment, I have a few words to say about infinite products. Now, we've already seen infinite sums in this series of videos, and here's what one looks like. N is a counter that runs from 0 to infinity. This is sigma, which is the Greek letter S, which stands for sum. It tells us that we're going to be adding up a bunch of terms. What terms? The terms are generated by the sequence a sub n. In this video, we'll be interested in infinite products. This n is still a counter that runs from 0 to infinity. And this here is capital Pi, not to be confused with the number pi. This is the Greek letter P, and that P stands for product. And it tells us that we're going to be multiplying a bunch of things together. What things? The terms of this sequence, a sub n. Why do I introduce this idea? Because the Wallis formula for pi is an infinite product. In this next segment, I present the Wallis formula for pi. It's nowhere near as good as the BBP formula that I presented 2 videos ago. But I'm presenting it here for 2 reasons. One, it's a formula for pi that's accessible to Calculus 2 students. In fact, a Calc 2 student can prove it, as I'll show in the 3rd segment. And 2, Wallis's formula for pi made the news due to a 2015 discovery in which the formula was derived not by mathematicians, but by physicists analyzing the hydrogen atom. The derivation of a purely mathematical formula such as this from the analysis of a physical system is astonishing, and it will be the subject of my 7th and final video in this series. This video will set us up for that one. John Wallis published the formula that is the subject of this video in 1656, and you can see it here. It's an infinite product. Strictly speaking, it's a formula for pi over 2, but of course, you can multiply both sides by 2 to get a formula for pi. Note the fraction inside the infinite product. The numerator is a perfect square, and the denominator is a difference of 2 squares. Consequently, it can be factored into this form. Plugging in the first 3 values of n, we see what the first 3 factors of the product look like. In this final segment, I'll prove the Wallis formula. It requires knowledge of Calculus 2, in particular integration by parts. Let n be a natural number. We begin by developing a reduction formula for this function I of n, which is given by the integral from 0 to pi of the nth power of the sine of x dx. We'll integrate by parts. U is the n minus first power of the sine of x, while we strip off 1 power of sine for the dv. The other 2 parts are calculated normally. Next, we plug everything into the integration by parts formula. In the next step, we'll use a Pythagorean identity to replace this cosine squared with 1 minus sine squared, like so. In the next step, we'll distribute sine to the power of n minus 2 of x over these 2 terms, and then separate the terms into 2 integrals, like so. This is called a reduction formula, because it expresses the original integral of the nth power of the sine of x in terms of the integral of a reduced power of the sine of x, n minus 2. Now this integral is I of n minus 2, and this integral is I of n. And so we'll make those substitutions. From this, we can deduce that I of n over I of n minus 2 is equal to n minus 1 over n. Next, we're going to deduce 2 useful variations of this proportion, one for when the argument of I is even, and one for when it's odd. First, the even argument. Let n be replaced with 2n. Then we get this proportion right here. And now the odd argument. First, let n be replaced by n plus 1. Then we get this proportion. And then replace that n with 2n, and we get this proportion. We'll need these in the next slide. Now let's check out 2 integrals that will be handy for this proof. The first is I of 0, which trivially evaluates to pi. And the second is I of 1, which is elementary and evaluates to 2. Next, we're going to take separate looks at the function I when its argument is even and when it's odd. First, let the argument be even. Here's I of 2n. We can use the proportion from the previous slide for even arguments of I to obtain this formula. Applying that proportion again yields the following. And we can keep on applying that proportion until we get down to I of 0. But we know what the value of I of 0 is. It's pi. So here's the pi, and this product of fractions can be collapsed down into this finite product using the big pi notation. Now let the argument of I be 2n plus 1, which is odd. We can use the proportion from the previous slide for odd arguments of I to obtain this formula. Applying it again yields this formula. And we can continue applying this proportion until we get down to I of 1. And we know that the value of I of 1 is 2. So here's the 2. And here's the product of the fractions using big pi notation. Now, the interval of integration is from 0 to pi. And when x is in this interval, the sign of x is between 0 and 1. This implies that larger powers of sine of x are less than or equal to smaller powers of sine of x on this interval. This in turn implies the following inequality for the integrals of these functions over the same interval. Now divide all three members by I of 2n plus 1. We know from 2 slides ago that the rightmost member of this inequality is equal to 2n plus 1 over 2n, and so we'll make that substitution. Now take limits of all three members and apply the squeeze theorem. The limit of 1 is 1, and the limit of 2n plus 1 over 2n is also 1. So we'll make those substitutions. And this unknown limit is squeezed between 1 and 1, so its value is also 1. Substituting the expressions that we derived for I of 2n and I of 2n plus 1 on the previous slide, we get this result here. We can eliminate the limit if we replace the finite products with infinite products. And in this step, I've divided these two fractions and put the quotient inside a single product sign. And finally, I multiply both sides by the reciprocal of the infinite product, and this completes the proof. Thanks for watching, and tune in for my 7th and final Pi Day video coming soon. Hey everybody, if you enjoyed this video and want to see more like it, then please do follow me on my socials. You know you want to.